should be recording. All right, let's get started. I wanted to go through a couple things on the homeworks for the past little bit. I know that, let me guess, the last homework, that was fun, was it? The inclined roller one? Yeah. I'm sure some folks will have some questions. I thought I would go ahead and spoil some stuff. I wanted to show you some things on the last homework on 2.1. So I know this won't show up on the recording, but that's no big deal. So first off, on homework 2.1, let me show you something. So for example, let's just take, a beam like this. It doesn't really matter. And let's say you have a triangular load, right? And let's make this distance, 9 feet. Okay. I collapse that into a single point load. Let's say that's 3 kips per foot. Okay. 2 questions. What is the magnitude of that load going to be? 27. Wait, no. I made up the numbers. I just made up the numbers. So 9 times 3 is 27 divided by 2, right? Because it's a triangle, right? So you got to remember that. So 9 times 3 is 27 divided by 2 is 13.5 kips. Okay, you got to remember to cut it in half. Okay, and what is this distance? 3 feet. Okay, this is 3 feet. That is 6 feet. Some of you were getting that backwards, and some of you were also just putting it right in the middle. Remember, the centroid of a triangle is 1/3 from the big end, okay? And then the magnitude is the area base times height over 2, okay? So some of you did like 27. I just made the numbers up, but yeah. Does that make sense? Okay. I did want to also show you some stuff on the homework that you just turned in. So 2.2, problem 1. So just to allay some concerns, okay, so here's the beam, okay, and there's a roller, and this angle is 30 degrees, right? Right? Okay? Now the cosine of 30 degrees is 0.866. The sine of 30 degrees is 0.5. Okay? The reaction is perpendicular to that surface, right? So when you split this up into x and y components, this one is the 0.66. This one is the RA, or the 0.5, okay? Because think, if this is at a 30-degree incline, then the reaction, the vertical component's going to be bigger, all right? Because it's not at that much of a slope, right? So the vertical component should be the bigger number. So if you can keep that in your head, you can sort of figure out which trig function goes where if you just keep the common sense component. Now, for this load here, there was a 50 kip load, and this was 4 to 3. The load is more vertical than it is horizontal, right? It's the vertical component is bigger, so this should be 40, this should be 30. So yeah. Same thing with problem 2. It's the same idea. Again, you're flipping those slope ratios. So with problem 2, the roller, I know that's sloppy. I can do better than that. So this, right? This is 3. This is 4. So whenever you draw your reaction, you flip 4 and 3. Okay. Now, what that means is you do not take the cosine of 3/5 or the sine of 4/5 or anything like that. No. Remember, the sine, the answer, the sine of the angle is 4/5, or the cosine of the angle is 3/5. So you don't take the cosine or the sine of the numbers because that's what that is. So this is going to be 4/5 RB, 3/5 RB. Does that make sense? I'll go ahead and tell you that today's topic's easier, I think so. And in terms of trig, this is, I mean, we're going to see some trig and whatnot here and there and here, but this is, I think, one of the more riddly, tricky trig exercises. It gets better. So, like with trusses, it's a lot more straightforward. It's much more systematic. Any questions on this? Does this make sense? Okay. All right. Let's go to the lecture. Now, I've got a couple of announcements. The lights work? Okay. All right. First off, you probably saw, or maybe you passed them or whatnot, but they're out there. There are some billboards in the hallway for an employer spotlight series. We're going to have some employers coming to campus. I know that you all are getting a degree for a number of reasons, one of which is I'm sure you'd like a job as an engineer. The first employer that's coming is the DOH. You all are civil engineers, so, that's kind of important. They're going to be here on September 8th. If you email Tanner Drown at Drown12 at Marshall, he's our co-op coordinator. There's only so many seats. It's open to the first 35 students that register, but students in our college are going to get priority. They're opening it up to basically everybody. I will be out of the office tomorrow. I will be back on Friday. I say that with a slight caveat. I will tentatively be out of the office. I'm supposed to go out of town, but then again, that's assuming the weather and whatnot cooperates. But I'll still be accessible via Teams and whatnot if you've got questions, which I've noticed that a couple of you are using Teams to message me, and that's great because it's easy for me to reach out. Sound good? All right. Oh, one other question. So on the homework that's graded, I want you to do me a favor. If you go to the grade center in Blackboard, you should be able to click your grade. So if you got like I'll make up a number. If you got like a 9 out of 10, you should be able to click that, and I've typed out comments as to why you got 9 out of 10 or 10 out of 10 or whatever. And if you got 10 out of 10 or what, you should just say like correct, great job or something like that. But I want to make sure that you can see that because I don't want you to go, why did he give me a 85 or a 70 or what? I want you to know why. So if you have any issues accessing that, let me know. Sound good? Okay. All right, let's add some more components to consider with support reactions. We're going to talk about, basically, today's lecture is all about one item, and it's about concentrated moments. Cantilevered beams are just beams that have concentrated moment reactions, so it's all kind of the same thing. Let's talk about what we've handled so far with reactions. And I mean, in a short time frame, we've actually handled quite a bit, mostly because what we're doing is we're taking all of these complex loads and turning them into point loads. And once you can do that, then you can use equations of equilibrium to determine reactions, etc. So far we've handled structures subjected to concentrated loads, we've handled distributed loads, and by distributed loads we're talking about uniformly distributed loads and linearly distributed loads. Now I will go ahead and mention on your homework assignment that's being assigned today, there is a problem that has a little bit of a funky distributed load. I'll mention it at the end. But what you can do is just sort of turn that into the same loads we've been dealing with before. And I'll show you that near the end. We've also assessed pin boundary conditions. We've assessed roller boundary conditions. And the rollers could be inclined. They could be perpendicular, what have you. So today I want to try and tackle that third boundary condition and look at another type of load event. And particularly, we're looking at concentrated moments. Now, with every new thing that I introduce, I'm really trying to do my best to ensure that there is a reality to it, that there's a real-life example, that this isn't just me throwing stuff at you to be complicated. Concentrated moments do show up in civil engineering structures, and they arise from really two scenarios. let me be clear. I don't want to come across as like the always and never guy. Like this is it. This is the only place you'll ever see them, because there's always some weird structure out there that could have concentrated moments on it. But most commonly, the two places that you get concentrated moments are from torsion into an adjacent member, or cantilevered supports, or anything with a fixed support. That's really the two places that you get concentrated moments. Okay, so I want to kind of look at this example here. Oh, that's right, I forget that. All right, I want to look at this example here. Let me see if the little screen laser pointer works. Hey, it works. Okay, so if you look right here, this is a floor beam, and let's say this floor beam is part of a like a canopy, or like a mezzanine, or a party deck or whatnot, if you will. And so you're out there, and there's this deck, if you will, that's cantilevered out from a building. So the floor beams are experiencing flexure, and what's happening is those floor beams are connecting to these spandrels, or these girders right here, and then these girders are framing into the column. If you look at the column, what are these floor beams doing right here? They're applying that sort of concentrated twisting action right there. Does that make sense? That here's the column, and right where that spandrel frames in, it's wanting to twist it in a concentrated fashion right there. Okay, so that's a concentrated moment that column would be experiencing from that floor beam. The other common place that you see concentrated moments are just the reactions of fixed supports. Now, some of the stuff that we introduce in this class, sometimes in addition to there being real-life examples of these, so there are real-life examples of concentrated moments, there are also instances where some of the tools that we introduce are necessary for later analyses to come. So for example, if you have a beam and it is subjected to loads, that beam will deform, okay? And that beam will experience both deflections, so literally how much it's going up and down, and then it will also experience rotations, like how much it's sloped. And in order to determine the rotations in a beam at a given point, you apply a concentrated moment at that point, and there's an analysis technique that we use to do that. So even if there's not a real-life example of a concentrated moment on the problem in question, you might need to understand how to deal with concentrated moments, because what you are interested in are deflections and rotations, etc. So understanding how some of this stuff works will prove useful later. All right, so what I want to do is I want to look at this problem. Okay, now this problem, if you just take stock of it, just about everything on this problem we've dealt with before. Okay, we have a beam that has a pinned support at A. It has a roller support at B. We have a distributed load on A. It's 10 feet long, 3 kips per foot, and we have a concentrated load at B. Concentrated load at the free end. If it wasn't for that pesky little 20-foot kip moment right here, this would be no different than any of the problems we've dealt with before, okay? It would really be no different. It's that moment that's making stuff weird, okay? So what we're going to do is we're going to handle this moment, and you're going to find that it's really simple, okay? It's really straightforward. So let me hit escape out of this. I'm going to pull the notebook up. See, there's no different. Everything here is the same. And I'm going to give you a second to draw this out. Okay, I'll give you a sec to copy this down, and then we'll get to it. And so, yeah, so this is 10 feet, that's 15 feet, and 10 and 10. Also, I was listening to one of these recordings for this class, and the microphone was coming out really loud, so I turned the volume down, so I hope that it comes out a little better. Then again, I'm just kind of loud in general when I'm in class, so. All right, everybody good? Okay, so first thing I want to do is I want to handle this like any other problem, okay? So what do I mean by that? We've got some reactions here. So let's identify those. We've got a vertical reaction here and a vertical reaction here. Okay? So we'll call this AY, BY, and then I have a horizontal reaction here at AX. I'm going to hold off on that one for a little bit. I mean, I could probably do it right now, but I'm going to hold off on that. All right? I have this 3 kips per foot. Let's deal with that. 3 kips per foot over 10 feet. I can collapse that into a single concentrated load that has a magnitude of 30 kips. And how far is that from A? 5 feet. Okay. Again, all we got to do is figure out that. So what I've done here with this 20-foot kips is I said we have a 20-foot kip, and the way that I drew this is I'm basically saying that 20-foot kips is being applied right there where that little crosshair is, and so that point of application is 10 feet from B, but you're going to see here in a little bit how that doesn't really matter, and that'll become clear in a bit, at least from a support reaction standpoint. Okay, so again, no different. We have sum of forces in the X direction, sum of forces in the Y direction, sum of moments. Same structure, same situation. So what I'm going to do is I'm going to handle this like we've done any problem up until now. I'm going to sum moments first. I'll sum moments at A. Let me put my little tick marks on my reactions. I forgot to do that. I'm going to sum moments at A in order to determine the reaction at B. Then I'll sum forces in the Y direction to get the vertical reaction at A. And then I'll sum forces in the X direction. We'll do that one last. Again, I think you can probably guess what it is, but I do want to leave it till last because I want to make a point about it. Okay. So let's start off. Let me scroll down a little bit. Sum moments at A. So we're going to sum moments at A, and basically what we're going to say is everything that's spinning this way equals everything that's spinning that way. No different. Okay? So let's do that. Let's start off. Do I have to consider AX? No. What about AY? No. What about that 30 kips? Yes. What side of the table, left or right? Left. Moment arm from A. 5 feet. There you go. So 5 feet. So 30 kips. 5 feet. All right. What about BY? Yes. Which side of the table, left or right? Right, because that is rotating in a counterclockwise fashion. From A, the moment arm is going to be 25 feet. Now we come to this 20-foot kips. All right. Do we consider it first off? Yes, it is a moment. We are summing moments. So yes, we consider it. That's easy. What side of the table does it belong on, left or right? Well, left. Now here's the kicker. What's the distance? There is no distance. That's exactly right. We are summing moments. That's a moment. So all you do is put 20. That's it. It's not 20 times 35. It's just 20. That was what I was saying earlier. It kind of does, from a reactions perspective, it doesn't really matter where it is. It wouldn't change the reactions at all. It would change your moment diagram, which we'll talk about later, but it won't change your reactions. Did I forget anything? Did I miss one? Yeah, I missed the 10 kips. On the left side, multiplied by a moment arm of what? There you go. So that's the big point I wanted to make, is that you do not multiply a concentrated moment by a distance. Like, it's not 20 times 35, because that is where it is. And if you do 20 times 35, take your hand, do that. No, don't do that. All right, so 30 times 5 is 150. 10 times 45 is 450. So 150, 450, 600, that makes 620. So therefore, BY is what? Do I have a second on that?
Yeah.
So there you go. Next, some forces in the y direction. Everything going up, everything going down. Let's be systematic about this. Do I consider the AX?
No.
AY?
Yeah.
Yes, AY is going up. What about the 30 kips?
Yeah.
Going down. What about the BY? Going up, and I know what that is. What about the 20-foot kips? Do I consider that? No, I don't consider that at all. This is not a force. It's a moment. We are summing forces in the y direction. That 20-foot kips doesn't matter. It's not a force. It's a moment. So just ignore it. And don't forget we have the 10 also going down. That's it. That's all there is to it. So AY plus 24.8 kips is 40 kips. AY is what? Is that 15.2? So now, with that knowledge in mind, what is the reaction at A in the x direction? It's 0. That 20-foot kip moment doesn't affect it at all. It's a moment. When I sum forces in the x direction, I have AX going to the right, and I've got nothing going to the left. So summing forces in the x direction, I get AX is 0. So what do you think? Is it better than trig?
Yeah.
Well, don't hold back. I mean, tell us how you really feel. Any questions? This isn't bad, right? All right. Let's move on. Let's do another one. Okay. Now, do I need to leave this up here for a bit? I see some folks still writing. Okay. Okay. All right. So let's go to our second source of a concentrated moment, and that's a cantilevered beam. Cantilevered beams are incredibly common in structures, just period. Any time that you have a beam, I mean, not to keep using the term, but anytime you have a beam cantilevered out from a support. Like, for example, in this upper image, we can see a column, or we can see this slab and see how it extends outward into space, and there's this beam here supporting it out in space. That's a cantilevered beam. For instance, if we were looking at a bridge and we were looking at these piers right here, I might treat this component of this hammerhead pier as a cantilevered beam and ensure that there's enough reinforcement right here to withstand the shear and moment right there at that support. That's a cantilevered beam, okay? Cantilevered beams are incredibly common. You're going to see them in balconies. You're going to see them in awnings. You're going to see them in bridge piers. They're just very, very common. And so understanding how they behave is very important. And one of the other things I think is worth mentioning is that from a reaction standpoint, they are incredibly simple to deal with. The computation of support reactions for a cantilevered beam is very easy, and you're going to see why. There's the equations that you have to solve are incredibly simple, okay? Especially if you set the equations up using this table fashion, they work really nice. Let's look at one. Oh, I threw an incline load in there. Like, oh, that's just mean, Dr. Mike. Why'd you have to do that? Oh, don't worry, it's not so bad. Okay. So we're going to compute the support reactions of this cantilevered beam. I've got a 20 kip load at the free end, and I've got a 10 kip load in the middle, but it's at an incline. It's at a 3 to 4 slope ratio. So we're going to do that one together to make sure that we understand how to split that up. Give you all a sec to copy that down. Everybody good? Let me pull the notebook up because it's got the same info. Oh, that's wrong device. All right. Okay. Now, let's start off with this 10 kips because we're going to do this one together, okay? This 10 kips is 3, 4, and that's 5. Okay, I think we're all in agreement with that. Okay, so, oh, go away. There's a vertical component and a horizontal component. Okay, what is the horizontal component? 10 times 3/5, right? Okay. And the vertical component is 10 times 4/5, right? And to be clear, what you are doing is, like, let's take the 3/5. What you are doing is taking 10 kips and multiplying it times the cosine of that angle. Because what is the cosine of that angle? Adjacent over hypotenuse, 3/5, okay? That's what you're doing. It's just shortcut, okay? So this is 10 kips times 3/5. This is 10 kips times 4/5. Does that make sense? Okay. Now, let's look at our reactions. This is a fixed support. How many reactions are at a fixed support? 3. Okay. There is a horizontal reaction. Which direction would you like me to draw it? Horizontal. To the right. Vertical reaction, up or down? Up. Okay, moment reaction. Like that? Let's do that. Let's do that. I'm glad you said that. I'm glad you said that for a specific reason. It's wrong. It goes the other way. Okay. Well, I want to do it this way, though, because we haven't done this yet in class. We haven't made an incorrect assumption, and so I want to do that. I want to make an assumption that's incorrect and see what happens, okay? Because this is once you start dealing with beams like this is straightforward. But again, when we start having structures with internal hinges and, so particularly with hinges, it is possible to make an assumption that's incorrect. And I want you to understand what that means, okay? Now, the computation of these support reactions is very simple, okay? So let's deal with, let me explain why support reactions for cantilevered beams are really simple. When you have a beam like this, you don't really have to be strategic about the order in which you do things. Like the last problem, let me go back to the last problem because I think this is kind of an important point, and we've got plenty of time. So with the last problem, we sort of have been doing this for a little while, but let's use our brains a little bit. Why did we sum moments at A? And more specifically, why did we do that first? To eliminate two unknowns, right? AX and AY pass through A. So by summing moments at A, we could directly solve for B. So there was a strategy to that, right? There's no strategy with a cantilevered beam. It doesn't matter what order you do it in. You can do sum of forces in the Y first. You can do sum of forces in the X first. It doesn't matter because let's take the Y direction. There's only one unknown. It's just that. So we could just solve for that right now. We could solve for the X component right now. I'm just going to do it in order. I'm going to do sum of forces in the X direction, sum of forces in the Y direction, sum of moments. See, for example, if you take the beam that we just did, the last beam, if the first thing that you did is sum forces in the Y direction, let's pull that back up. This is kind of important. Let's look at this beam. Let's say that we summed forces in the Y direction first. So we would get AY going up, BY going up, and we get 30 and 10 going down. So if we sum forces in the Y direction first, we would get AY plus BY equals 40 kips. We wouldn't know what AY and BY were. We would just know that adding them together, we'd have to get 40 kips, right? So what we would then have to do is say, okay, well now let's sum moments, get one of them, and then plug that value into the equation to get the other, right? It's more cumbersome, right? If you do the sum of moments expression first, you have BY, and so when we get this, we get AY plus BY equals 40. We already know what BY is, so it's a lot less runaround, right? It's more direct. We don't have that problem with cantilevered beams. I just want to make sure that that's clear. Which, by the way, we are going to have problems in here where we have two equations and two unknowns. And in those instances, you definitely want to bring your Casio FX115 ES Plus and not your iPhone X10. I'm an Apple guy, so I don't know iPhones. But you definitely want to bring a calculator that has a 2x2 equation solver because you will need it. But that's for later. Okay, so let's do this in order and let's see what we get. All right, so if I sum forces in the X direction, just everything to the left and everything to the right. So I get AX to the right, 10 kips times 3/5 to the left. And if you want, we could just say 6 kips. And so what do we get? AX is 6 kips. And we got a positive answer, so that means it is going in the direction that we assumed, okay? That means it's going that way. Sum of forces in the Y direction. So what do I have? AY going up. What do I got going down? 10 kips times 4/5 and 20 kips. So what's AY going to be? 28. Positive. And what does that positive value in that expression mean? It means we assumed AY to be going upwards. We got a positive number. That means that assumption was correct, and 28 kips is going up. That's why I've been writing the expressions like this. I've been saying AY equals positive 28 kips, which means it's 28 kips going up, because the positive indicates that the direction that we assumed up here was correct. Okay? Now we're going to get something a little different with the moment expression. Now I'm going to sum moments at A. I'm still going to do that because even though I don't have to be strategic, if I sum moments at A, then this and this pass through A, so I don't have to deal with it. Okay? So, let's start. Do I consider MA? Yes, it is a moment, right? So what side of the table does it belong? Left, because I have it drawn like this. So MA. Okay, this 10 kips. Let's see, do I consider the horizontal component? No, right? Do I consider the vertical component? Yes. What side of the table does it belong? The left. And what's the moment arm? 10 feet. So I have 10 kips times 4 fifths times 10 feet. What about the 20 kips? Do I consider that? Yes. Left or right? And what's the moment arm? 20 feet. So 20 kips. Do I have anything over here? No. Uh-oh, Raggy, what do we do about that? Give up. That's funny. No, we don't give up. Come on. All right. This is a sum of moments expression, so we sum moments. What do we have on the left? What is 10 times 4 fifths times 10? 80. 80 plus 400 is 480. So MA plus 480 on the left. And what does that equal? 0. Because there's nothing on the right. So if I solve this equation, what do I get?
Negative 480.
Negative 480. So now I get that MA is negative 480. And what does that mean? That means that this assumption going in this direction was wrong. That's all it means, okay? So I assumed that this would be 480. What did I assume? I assumed clockwise. That means it's 480 counterclockwise. That's all that means, is that the assumption in the direction was incorrect. That's all. You don't need to develop significant emotional distress. Just means that your assumed direction was incorrect. And that's very possible when we start dealing with beams with internal hinges, because there's going to be, so if you have a beam with internal hinges, you might not have 2 supports. You might have 3 supports. And so you might have 2 upward reactions and 1 downward reaction. That's very possible. And sometimes when I'm doing those problems, if I have a beam that has multiple supports, I just assume that they're all acting upwards. And so if I ever get a negative answer, I know it's acting downwards. So I don't try and be Nostradamus and try and go, well, that looks like it's acting upwards. Just let the math figure itself out, you know? I find that easy. Sometimes when I'm doing truss analyses, and we are actually going to do this when we start doing 2x2 solutions, is we're going to assume all the members are in tension. And if we get a negative answer, that just means it's in compression. So it's actually easier on us as analysts. So what's your answers? AX is 6 kips that way. That. Oh. Answers. And before we leave, I'm going to show you a hint on your homework assignment real quick before we leave for the day.
That's like AZ instead of like MA.
Sure.
Technically correct.
What's that?
Is that technically?
I would say no. First off, I'd say no because AZ could be, like if you're doing a 3D analysis, it could be a force. You can write MZ, but then it's MZ at A, just write MA, you know. I probably wouldn't, but I'm also not a micromanager in terms of the notation. I never have been, you know. All I would say is that if you were submitting those calculations to me as a reviewer, I might do, you know, I might go, what? You know, but that's fine. Any questions? Okay, I want to pull something up with the homework assignment because I put some hints with the homework assignment and I kind of want to explain them. And then we're going to call it. So let's see. So here's your homework assignment, and there's 2 problems. One of them I think is going to be pretty straightforward. The other is not hard, but I'm afraid just because of the way the problem is drawn that you're going to think it's hard, and it really isn't. So I want to talk a little bit about problem 311, and I want to explain these 2 hints. And so I'm actually going to do this in the class notebook so that you have it. What's that? It's homework 2.3, right? I think, yeah. Okay. Okay, so the first thing to note is that if you actually look at the beam, the way that it's drawn in the book is it's sort of drawn like this, and then it's something like that. Like that's how it's drawn in the textbook. That doesn't matter. You can treat the beam like this. It wouldn't affect your results anyways, even if you did treat it like that, but you aren't given any dimensions anyways. The reason that we construct beams like that, that's called a haunched beam, is because of the moments. The moments are higher at the supports. So in structural engineering land, the deeper a beam is, the stiffer it is, which is why we have deeper beams whenever we have higher moment demand. Think about the bridges crossing the Kanawha in Charleston, those big old truss bridges. Look at them. You know how they go like this, how they point up? They do that at the piers because the moment, if you will, is larger there. So just food for thought. But the real thing I wanted to get across for the hint is this. So there is a load on the beam, and please do not quote me on the dimensions or the numbers because I don't remember them offhand. That's why I put it in the text of the homework assignment. But it does something like this. So it's like 2 kips per foot, and then it jumps up here from 2 to 3 kips per foot. So that's the load that's applied. And what I'm suggesting that you do is treat this like two separate distributed loads. So this is sort of what I'm thinking you should do to keep it simple. Is you have one load that goes like this, and then another load that is a triangular load like this. And the magnitude of this load is 1 kip per foot. And the reason why it's 1 kip per foot is if this is 2 and that's 3, then that difference is 1. Does that make sense? So I don't think that this is that big of a deal, but I don't want this to be the barrier for handling the assignment. The purpose of the assignment is to be able to handle the concentrated moments, and I don't want that to be the easy part. It's like, well, I still don't understand this. So I thought this was a reasonable hint. Because, yeah, just to clarify here, so it's on the drawing, this is 2, and that's 1. I didn't tell many jokes today. I have some really good jokes about structures. If I tell you, I'm pretty sure I'll get a good reaction out of you. All right, any other questions?
I don't think that was the right moment.
That wasn't the right moment for that joke. Ha, 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 ha. That was really good. All right, that's all I have, everybody. I'll see you all on Friday. All right, again, just message me via Teams if you've got questions about your homework.